Hello. Today we are going to talk about a very important topic of terahertz vacuum electronic devices. Now let's look at the outline of the talk. I will introduce the topic, then move over to the various application of terahertz radiations, and let's discuss the terahertz vacuum electron device sources of various types, their underlying principle, their technology, and their challenges, and then we'll finally make a conclusion by looking at the various kind of sources, the capabilities they offer, and the kind of challenges which lie for their future development and application. Now let's look at the terahertz radiation. Now the terahertz range of radiation lies actually between the infrared and the microwave range. And the first scientific paper on this particular band was published in the Physical Review in 1890s, the very first issue actually. But still today, it remains the least used region of the electromagnetic spectrum. No doubt, there has been a significant amount of activity for last 2 to 3 decades in this area, and much of it currently is being driven by the communication and ISM applications. Now, let's define what we talk, what we say is terahertz frequencies basically. From 300 gigahertz to 3 terahertz is considered the terahertz band. Some people extend it to 10 terahertz also, but we will confine to 3. The wavelength at those frequencies is pretty small, from 1 millimeter to about 100 micrometer. The energy of the photon is also fairly small, 1.2 to 12.4, and at that energy, the radiations still remain non-ionizing, unlike the X-ray and the gamma rays. These photons are still in the non-ionizing category, and this energy corresponds to black body temperature of 14 to 140 degree Kelvin. That means that anything above 14 degree Kelvin will emit terahertz waves. Now let's look at some of the applications of terahertz which are quite prominent. And the first and the foremost application of terahertz frequencies has been in the field of molecular spectroscopy. The astrophysics people from who study Earth, planetary motions, and the space sciences and the galaxies and universe have been using the terahertz telescope for quite some time, sub-millimeter wave telescope for quite some time. Then it has also been used for environmental monitoring for greenhouse gases. The ozone hole mapping has been done using terahertz waves. And there is a very interesting application of plant water monitoring. That within the plant, how the plants distribute the water among the leaves, in the branches, in the stumps, and so on, has been very beautifully studied using terahertz wave. Because water is a very good absorber of these frequencies. In the field of imaging, the terahertz has been used for quality control of semiconductor packages, for manufacturing, in food industries, in product and packaging control. While the food is packaged or the item is packaged, you can still see it, which is not possible to do it with the X-rays, for example. And these are the things which can penetrate glass, fibers, cloth, plastics, and anything, and can create their images. The other application come in the field of plasma diagnostic fusion, which is a very important application in the field of energy. Then in the field of biomedical imaging, because terahertz can penetrate the biological tissue to about 1 millimeter depth. So it can be used for diagnostic of cancer, dental applications, then enhancing the nuclear magnetic resonance images by DNP, dynamic nuclear polarization, and the analysis of the DNA are some of the biological imaging applications. In the field of defense and security, the concealed weapon detection is one of the very good application of the terahertz waves for passive kind of detection of any concealed weapons or contraband items. And there are applications in miniature radar, all weather navigation. For example, in a combat scenario, in smoke and dust, you can see through using terahertz waves and navigate. Then the remote explosive detection is a very important defense application or security application. And the killing application of terahertz is actually the high data rate communications for 5G, 6G, and beyond. Now, this is a slide which is from Roland Schwartz, and this says that new spectrum for 5G and beyond is going to have a huge frequency spectrum available at millimeter wave and terahertz frequencies. And if you see in the bottom in the 6G, then you find that the H band from 250 to 325 has been assigned by IEEE standard for point to point links. The World Radio Conference in 2019 has identified land, mobile, and fixed service applications from 275 to 450 gigahertz. So these are only some of the things which are projected now, but as things take shape, there may be more refinement in the frequencies and band allocation, etc. But it is specifically true that there is going to be fairly good requirement of terahertz frequency devices, components, and technologies of all kinds to make the systems at these frequencies viable. Now let us look at the terahertz generation. If you have to actually produce any terahertz system, the very first thing that you have to have is a very good source. Now, what are the sources of terahertz generation available to us? So here, one of the very basic source is a black body, basically a thermal source which gives a black body radiation over a very wide frequency, but the power is extremely low. Then we have the solid state devices like gallium arsenide, gallium nitride, or indium phosphide, and so on. Now, all these devices have a good performance at terahertz frequencies, but they offer very, very low power. Then we have the main workhorse in the high power RF microwave, which is the vacuum electronic devices or microtubes. And these are fairly mature devices. They also work at high power. And there are a few specific sources in the VD family, like backward wave oscillator, BWO, the extended interaction klystron, the gyrotron, and the free electron laser, and a few others which have found very good possibility of generating terahertz frequencies at very good amount of power for various applications. Then combining the solid state and the vacuum electronic technology, a new field of vacuum microelectronics is emerging, and that is a necessity of the terahertz requirement because at these frequencies, as I mentioned, the wavelength goes into hundreds of microns. And the vacuum electronic devices have dimensions which is scaled down with the wavelength. So as the wavelength decreases, the dimension of the device also decreases. And it is, uh, let's say, lambda by 2 or a fraction of the wavelength. So this is going to be smaller than hundreds of, less than a millimeter or a few hundred micron. Now, fabrication of such small, tiny circuits become very difficult by the bulk machining technologies, and that's where the microfabrication techniques followed by the solid state devices and the MEMS technology come into play. So there is a new field of technology emerging which utilizes the microfabrication techniques of solid state devices and the motion of electrons in vacuum and similar kind of format as we have in VDs for traveling wave tube and BWO in planar format to give rise to new kind of microfabricated devices. Now these devices have promised to offer low to medium power and they are no doubt in initial stages, but already some of the finished devices started coming out and have been used in some systems for testing at least. Then the other important technology is the photonics technology, and which is fairly well established and sufficiently good amount of power at terahertz frequency is already available from the quantum cascaded lasers, photomixing, synchrotron, and the frequency multiplier, and so on. So we will now compare these various technologies and see that why we should focus so much on vacuum electronic devices. Now here we have a plot of frequency versus average power in watts, and then this is comparing the four technologies of the vacuum, solid state, photonics, and lasers. Vacuum microelectronics is also covered under vacuum. So if you see here that the highest power comes from the gyrotrons. So these are basically having almost a kilowatt of power here. So the highest power horses are the gyrotron devices. Then comes the extended interaction klystron. Then after that, if you see, comes basically the grating vacuum devices, Eurotron, etc. Then come the micro machined traveling wave tubes, backward wave oscillators, which we are going to discuss in this talk. Coming to the uh, photonics or lasers, we have the highest power at the highest frequencies coming from the optically pumped molecular lasers. The quantum cascade also have good amount of power at very high frequencies, and the solid state devices have a very wide coverage over the frequencies, almost 3 terahertz, and but their power is remains moderate, maybe very few, you can say microwatts to half a watt at the most in the lower frequencies. So this is a challenge, but solid state devices being very small, you can also combine devices. You can have MMICs which combine a number of such devices and so on. The photo mixing technologies or photonics technology work at a broader frequency range but at much lower power, but they have their own applications. They will mostly confined to the VEDs for the specific reason that they offer very high power and they almost cover the required band. Now, the vacuum electronic devices are the most reliable electronic sources. I come from that area, so I can vouch for it. And they can deliver from kilohertz to terahertz, very wide frequency span. And their power levels also can go from milliwatt to gigawatt. Of course, not simultaneously, these two things don't apply. You can't have gigawatts at terahertz, but these are the extreme limitations of the devices. Now, let us discuss these devices in detail. Now, vacuum electronic device, when we say, we remember the tiny walls. So, the very first electron device was a thermionic diode patented by John Ambrose Fleming in UK in 1904. It was based on the Edison effect, which was discovered in 1883. The first demonstration of the electrical wall, one-way electrical wall as a detector to convert radio waves into a flow of current which you can measure with a galvanometer was done by Fleming. And in my view, this invention basically heralded the dawn of the electronics area. And vacuum electronic devices have never looked back from that point and have been growing for more than 110-15 years, and they have reached various improvements in performance and variety of devices, a variety of applications have been built. Now let us look at the fundamental operating principle of a vacuum electronic device. Now if you see here, this blue boundary is some kind of a closed envelope, a vacuum envelope as I call it, and inside this envelope there is a good amount of vacuum. And we have a circuit which is carrying a micro signal or a terahertz signal maybe, and then we have introduced an electron beam. So the operating principle basically lies in propagation of a focused electron beam through an RF circuit. And when you do that, what happens is some mechanisms happen and conversion of the electron beam energy into the RF fields takes place. And initially you might feed some power if it is an amplifier, and you can get amplified power output. However, if you have an oscillator, you don't need to feed any power. From the noise level, the power in the micro device grows and comes into significant amount of output power. Now, what really happens in this device is that when the electron beam goes through a circuit, the electron velocity is modulated by the RF fields on the circuit. Now, when the electron further passes through into the circuit, the transit time effect causes current modulation of the beam. So the velocity modulation results into current modulation or density modulation of the beam, and we call it bunching. Now this bunches as they proceed in the microwave circuit, they introduce or induce RF fields on the, so this conversion of a space charge field of electrons to RF field on the circuit starts taking place. And in this way, the beam actually generates or amplifies electromagnetic waves on the circuit, which is then taken out from the output. So this is a very basic and in simplest term, a common underlying principle of energy conversion of electric energy to high frequency RF microwave terahertz by a vacuum electronic device. Now, this energy could be electrical energy, which is in the form of kinetic energy of the beam, or the potential energy of the beam. Either of the things can be converted depending on the format of the device. Now, there are two kind of formats of the devices that we have. One is a linear beam device, also called O-type tube, after a French name of the device. And in this, you find that the electric field and the beam are parallel to each other, the direction of these two, and the magnetic field is also parallel to each other. So both, all three, electron beam, electric field, and magnetic field are parallel to each other. And such device configurations are called linear beam tubes. On the other hand, we have a configuration in which all the three, electron beam, the electric field, and the magnetic field, are all at right angles to each other. And this kind of device is called as a cross field device, or M-type tube, after the French name. Now, having told about the basic operating principle, I would now like to describe you the construction of a specific, a typical vacuum electron device. So here we take the basic elements of a vacuum electronic device, and I have chosen a helix traveling wave tube because this is something which I have worked much part of my active life. So here you see that this is a linear beam device. It's a elongated thing, and there it has a very rugged envelope, and in which it is a cutaway view what we are seeing. So here at one end we find that there is a cathode which is emitting electrons, and then there is an arrangement of electrodes which we call as electron gun, which is giving out a pencil shape of electron beam. Now this electron beam is going through a helical circuit or a helix, which is a RF circuit, and then this after it crosses the helix, it gets dumped into a region called collector. Now, when we feed the RF signal in, as I just described in the earlier slide, and the electric field is already established at the helix, the interaction, as described earlier, will take place between the beam and the RF fields on the helix. And at the end, the amplified output will be taken out. Now, there is one more element here, that this beam under the space charge forces will try to diverge and go away from the, or touch the helix and so on. So we have to keep it confined so that it doesn't get intercepted at the helix. So there is a strong magnetic field used here in this region to keep the beam confined. The other thing we'll see is that this is a very hot region because cathodes are mostly thermionic cathode. They are heated at 700 to 1000 degree temperature and degree centigrade, I mean. And here in the collector region, the heat is dissipated. The spent beam, after having given output, has still a lot of energy which get dissipated, and so this is also a hot region. So in a microwave tube or a terahertz wave tube, what we do basically, the RF interaction region and the heat dissipation regions are separated. And the construction also is modular. You can build electron gun separately, slow structure separately, gun separately, and collector separately, or coupler separately, and combine all these together to integrate a full device. Now let us have a little more detailed discussion on each of these things here. So one is that there is a sealed off envelope with ultra high vacuum for collision less ballistic of electrons, and the vacuum is better than 10 to the minus 7 torus. Now let's look at the electron emission part. The cathode could be a hot or a cold cathode, quite often a hot cathode, but in terahertz devices, people are now trying to also have cold cathodes. So it could be thermionic cathode if it is hot, and if it is cold, it could be a field cathode, field emission cathode, or a photo emission cathode, or it could be a plasma emission cathode. Then there will be a high voltages and arrangement of electrodes for acceleration of electrons. So basically that we call as a either a diode region or a electron gun. So if we want a pencil shaped beam or a strip beam or a hollow beam or a multiple beamlets, basically giving a big bunch of beams, small beams, then all these formats are possible, and you can have a corresponding type of electron gun to generate those kind of beams. Now coming to the focusing, the magnet system for electron beam focusing could be either an electromagnet, it could be a permanent magnet, or it could be a superconducting magnet. Now here the magnetic field is used for focusing the beam, but in M-type devices, the magnet is used also for device operation. So there also you can use either of these type of magnets for creating the required magnetic field. Now coming to the microwave circuit in this, now if you look at this figure, from this RF input to RF output is what we have the RF circuit. So there is a input RF coupler which and there is an output RF coupler. These could be coaxial and waveguide, or both could be coaxial, both could be waveguide. Then you have the Slovene structure, which could be either a helix or a helix derived structure like a ring loop, ring plane, etc. Or it could be a series of open cavities or resonant cavities, or it could be a series of coupled cavities, which is a slow structure. And then there is an important thing here that when the microwaves have to come out of this vacuum region to the air region, then we need a window here, a microwave window which passes microwaves but holds the vacuum. And so this is a very critical part, and it is often prone to failure, is a microwave window. Now coming to the electron collector, if you simply have a grounded collector which is at ground potential, and then will simply dump the electron beam and dissipate all energy of the beam into heat. So that is a single stage collector. But what we are seeing here are multiple stages. Yellow plates are multiple number of plates, and each of them at different potential. So this constitutes basically a multi-stage Diplex collector. And it is also called an energy recovery collector. It recovers energy from the spent beam and feeds it back to the power supply. And in this way, it is used to enhance the overall efficiency of the device. Now coming to the cooling system, because we mentioned that there is a lot of heat generated here, both the regions, and also some heat is generated here in the middle region due to the RF losses and some electron beam interception losses, because whatever we do with magnetic focusing will not be able to transmit 100% of the beam, and some part of the beam will be intercepted by the circuit and result into heat. So there are various kind of cooling systems. It could be either conduction or convection by liquid or air, or by radiation into space. And this is one which is used most uh, effectively in outer space. And then you have to have a very structural, rugged packaging of the whole thing to maintain the integrity, alignment of the device, and all these components, and to let the device perform in the most testing of the environment of shock, vibration, humidity, and all kind of environmental factors which the systems in which the devices are put go through. Now, I'll just summarize some of the unique features of the VEDs. So, collisionless ballistics is a very, very important function we already told, and they have very high peak power, can going to almost hundreds of watt to kilowatt, as we already mentioned in the terahertz range. Then yeah, they can have very wide bandwidth of 3 octave that may not apply on terahertz, but in general you're going to have high efficiency from 20-30 to almost 70-80%, high gain to almost 30 to 60 dB, modularity of construction of the defined, and vacuum electronic devices have very long life. Some of the space utilities are guaranteed for 15 years. And they are naturally having radiation resistance because having bulk of metal and which will absorb radiation, and good thermal management. But they also have disadvantages that they require a huge amount of magnetic field, because of which the device becomes bulky. The device may be small, but magnetic field takes quite a bit of weight. There is no standard product range. You have to build a specific device for specific application. Their manufacturing cannot be automated like semiconductor, that you have one big uh, wafer and you can have thousands of devices on that. Here you have to craft each device separately. Some limited automation is possible, but at assembly level, it still becomes manual. And that's the reason their cost is also very high. The only thing which has been done cost effective is the domestic oven magnetron, which is done in millions of numbers by automated manufacturing process. So if the numbers are there, maybe other devices also can be done the same way. Now let's look at some of the Terra's devices, which will have go into detail. That is the BWO, extended interaction Gladstone, and gyrotron devices, and some of the microfabricated devices. So these four will cover this talk, the time permits. So let us look at the first one, the backward wave oscillator. Now this was proposed in the 1950, that Millman found that microwaves can be generated by interaction of an electron beam with a forward wave. Before him, Komfner and all others have done TWT, which was using a forward wave. And in other forms, the device is quite similar. But let us look at what are the forward and the backward wave business which we are discussing. Now here is a dispersion diagram on the right of a slow wave structure. So which is a periodic slow wave structure, which could be interdigital line or a corrugated waveguide or a folded waveguide or a slotted vein or grating, any kind of waveguide, but it has a periodicity and slow wave characteristics. Now the dark regions here are the forbidden regions. Here no propagation takes place, and this curve which you see here is the positive branch, and this is the negative branch of the dispersion curve. Now, the straight lines which we see here are basically the lines corresponding to electron beam. Okay? So the velocity or the voltage of the electron beam is different here. It is higher and it is lower here. So they are different voltages basically. So sorry. So if you see here that this point of interaction of the electron beam line and the dispersion curve of the solar circuit, both the phase velocity and the group velocity are positive. But at this point, if you see that the phase velocity, though positive, the group velocity is negative. And for this region, this particular mode, if the beam is interacting at this point in with the device mode, then this is a backward wave mode. The energy will be traveling in the reverse direction, in the negative direction, and the beam will be propagating in the positive direction at this point. So this is what Millman found, that even at this point you have microwave generation. So a circuit supports both the forward and the backward wave, and for a BWO the electron beam is basically synchronized with the backward wave, and the energy propagates in the direction towards the cathode. When we look at the device geometry, you'll see that. So let us look at the device geometry. So here is a backward wave oscillator in three-dimensional, basic 2D cross section basically. So here you have like similarly as I showed, heater and a cathode forming electron gun and forming a lead pencil type of beam, which is going inside a corrugated waveguide, which is a periodic slow structure, and it is the situation between the device parameter and the electron beam velocity have been so adjusted that there is a back wave word wave interaction taking place, and there is a magnetic circuit to keep the thing electron beam focused. Now, as you see here, the electron beam as it progresses, it forms into bunches here, tighter bunches take place here, but the power is traveling in this direction and the RF output is taken from here. Here at the input, we might have a batch load or may not have anything, and the dissipated electrons go into the collector, and if it is a multi-stage collector, they will have further energy recovery there. So this is an O-type BWO. You can have an M-type BWO where the field, this is a planar geometry basically shown here. So this is a row of comb type of a slow circuit or a meander line type of slow circuit, and here you have a beam which is being bent to this direction, and so this is a soul which is negative potential. Between these two, the E and B and the electron beam, all they are at right angle to each other, and in this kind of a device you can also have the backward wave oscillation. So the O-type device was done by Kompfner, and M-type device was also called carcinotone, was done by Epstein and Thomson, which is now Thales, and higher power BW. BW is a very versatile device. So relativist BW generate up to gigawatts of power at lower frequency, and the gyro BWO, which is another type of device, uses a hollow beam, which we'll discuss in later, and can also have medium power at terahertz. Then there is a planar micro machine version of the BWOs, which is planar, which I mentioned from the vacuum, uh, uh, mic, sorry, microfabricated vacuum device kind of a format, and this we'll discuss later separately. Now, the soil structure already mentioned that it could be any of those types, and the electron beam can be a pencil beam, a sheet beam, or hollow beam, depending on the format of the device. Now, these basic features of the BW are that they are very highly stable oscillators. If there is a variation at the input from the uh, but I mean where it is antenna and other things are connected, if the load variation takes place, even then, because the device is configured in such a way that it does not influence the happenings where the micro is getting generated, and for this reason they are highly stable in frequency. They can also be tuned in voltage, as I showed here, that if you move this point, then you can have a huge variation of frequency, because this is a very steep curve here. If you move here, you can have a huge variation in frequency. So they can be changed by changing the frequency, so electronically tunable, and bandwidth as high as 50% is possible. But they suffer from a major limitation, that they have a very high, very low efficiency. And for this reason, even though they are useful, they still find good applications, but this is one of their limitations, inherent limitations. Now there are variants of BWO produced to overcome this efficiency limitation. So basically, the reason is that in a in a slower circuit, the fields actually propagate very close to the surface of the structure. So beam also has to be close to the structure. And for this reason, there are challenges which come here. And to overcome those challenges, there are new type of circuits which have been proposed, like Horotron, for example, which uses a Fabry-Paro cavity of two mirrors. So there is a corrugated kind of a grating here, and uh, there is a spherical mirror. This together form a cavity, and the electron beam propagates like a strip beam over the grating. And this device offers higher volume, so you can have larger beam power, and you can have a larger power. And this is also mechanically tunable as well as electronically by beam voltage I mentioned, and mechanically by positioning the spherical mirror up and down, and the output is taken from the hole in the mirror. And it could be done in a cylindrical configuration, linear beam, or in a planar configuration. There is another variant of Horotron which is called Clinotron, and it also offers much higher power than this. And in this, they use a thick tilted sheet beam. The electron beam is thick as well as tilted, so the interaction between the beam and the RF waves, which are close to the surface of the grating, takes place more intensively. Interaction impedance is high, and that offers higher power. So BWO have a lot of applications as local oscillator and fast tuning receivers, in terahertz imaging, and in interferometry for plasma diagnostics and many other applications. So here is a comparison of the performance of the BWO devices, BWO, Clinotron and Orotron, and you see that they go almost to about 100 tens of watts of power, and almost to 1200 to 1300 gigahertz, that is 1.3 terahertz. The technological challenges that we have is because of a small size, there is difficulty in fabrication. RF wave very close to surface, I already mentioned. They require very high current density, 50 to 100 ampere centimeter square. And at that density and close contact, the beam interception and circuit erosion is a big problem. And the strong magnetic field and uniformity of field and beam focusing is a very critical aspect. And when heat dissipation from such a small component is to be done, then the thermal management is also a challenging task. Now, just the last slide about the BWO. Here it shows these are the these are the BWOs done by Russians. Company stock sold to Alva, and these were done even before the terahertz became so popular in the Western world, and they have a very good performance right up to 1250 gigahertz. As you can see, about 2 milliwatt performance here, and 50 milliwatt at about 260 gigahertz in this range they offer. And they are very compact devices. They are work at very low voltage of 1 to 4 kV, 6 kV, small current of about 60 milliampere mostly maximum, and their weight, which is mostly magnet, is about 15 kg, which can be reduced to some extent by optimizing from high density magnets. And so then we'll move to the other topic of the EIK. So I'll stop here for some while, some time.